Section 4.3, Maxima and Minima. That is means what is when a function has the highest or lowest point is what we're concerned with in this particular chapter. There is the absolute maximum, which is by the meaning of the word means that's the highest point the function can get. And similarly, absolute minimum. All right, that's good enough. Next page, let's look at page 367, where you have various functions that has various situations. As you can see, some of the functions, like that one, that's like y equal to x cubed. Yep, it is. Where it doesn't have an absolute maximum minimum because, well, it goes on forever, right? Both directions. Whereas other functions might top out at some point, like this one. But anyway, so that's all pretty obvious. So let's move on to the extreme value theorem at the bottom of the page 367, which says that if f is continuous over a closed bounded interval, what is closed bounded? Closed means it includes the endpoints, okay, and bounded means is not infinite. So if f is a continuous function over a closed bounded interval, then there is now for us a closed bounded interval just means some random some interval that starts at 2 points and contains its end points. That's all we need to know for now. Okay, and so then in this case, then the f will have an absolute minimum in here. If you have a function that's continuous in the closed bounded interval, then the function will have one absolute minimum at least and one absolute minimum in this closed bounded interval. And in other words, being that the function is continuous the way through, it can't take off into an asymptote, okay, because it's continuous or do some other odd thing. You will have at least one maximum or one minimum that you can locate. Now, that is pretty obvious intuitively, but though it will be proved in advanced mathematics, which we're not going to concern ourselves with right now. The theorem only works if f is continuous through this interval we're talking about. So next page, let's consider a local maximum or minimum, which is what we are more concerned with most of the time. A local maximum is when your function has a slight hump locally. That locally means in the immediate neighborhood, without considering later. I mean, later this is a local maximum. Later the function might go up to rise to new heights, but locally, for this particular small area, we see that it has a maximum. Similarly, it might have a small minimum somewhere and then maybe take a dip later, but we don't care. If it take a small dip and go back up, then we call it a local minimum. And that is a fairly intuitive definition of what a local minimum or local maximum is. And then we say that f has a critical point then if f prime equal to 0. Okay, the critical point is just if f prime is 0, or even if f prime is undefined at a certain point, then we say that f has a critical point at that time. In other words, whenever the derivative is 0, then it might be f is probably has something happening there, or if f prime is not defined, something interesting might be happening here. So we call that a critical point. Now the next theorem, Fermat's theorem, is what's useful. If f has a local extremum, a local one, all right, and f is differentiable at that point, then the derivative of f at that point has to be 0. Now, if you consider this fact, if f has a local, we're talking about local, right? A local max or local min, then it does make sense that it is the derivative is 0 at that point just by looking at it. But now we're going to actually prove it, and the proof turns out to be fairly simple. Now, so we will do the proof. This is on page 369. We'll do proof Fermat's theorem 369, which is if f is differentiable at a certain point, then the derivative at that point is 0. Now, how will we prove that? Now, to prove it, first we will consider the derivative of f at that point that we're talking about. So, by definition, f prime at the point that we're concerned with, let's call it c, because your book does, is we'll go back to the old definition of the derivative, which is the limit definition. As x approach c, f x minus f of c over x minus c. All right, that is just the definition of the f prime of c. Now, what we do know is that, what do we know? It has a local, let's say it has a local maximum. Okay, we'll pick this one. The minimum proof is identical. So we'll prove just for the maximum. Let's say c is a maximum. Okay, so we'll write that down. C is maximum. A local one, which means locally in that delta, locally means the delta neighborhood. Okay, remember our cute little delta neighborhood? In the little delta neighborhood, everything in there, f of c is biggest. In other words, within that delta neighborhood, f of x minus f of c is going to be less than 0. Is it less than or equal to? It's less than or equal to is fine. Yeah, it's less than or equal to 0 because c is the maximum. So everything around it is going to be less than or equal to 0. Now, knowing this, then the next thing we're going to do is this fact. Is go back to the definition of limit. We'll consider left side limit and the right side limit. Remember the left side limit? The left side limit is we're approaching c from the plus side. Okay, so we're going from the right side, and the same formula, right? F of x minus same thing, f of c divided by x minus c. But this is the left-handed limit. Now the left-handed limit is going to be what? That equals to it still equals to f prime of c, because the definition of limit says if the limit exists, then the left and right side has to be equal. So that was still equal to f prime of c. Okay, now at this, being that we're approaching c from the plus side, x is bigger than c. Okay, and being that f of x minus f of c is less than 0, this value is less than 0. Well, this value is positive. So that's negative, that's positive. So this whole thing is going to be less than or equal to 0, right? Because the way we're approaching, and c is a maximum. So that relationship exists. Now, similarly, so far we have proven that f prime of c is less than or equal to 0. Now, similarly, now we are going to approach from the negative side. So limit as x approach c from the minus side, that is from the left side of the same function, f of x minus f of c divided by x minus c. Now, what happens when you approach from the left side? From the left side, x is less than c, so this is a negative number. In the meantime, this value is still less than 0. So this whole thing is going to be bigger than or equal to 0. Okay, because this is negative, that's still negative. So together, negative means positive. And this is still equal to f prime of c. Oops. Well, that looks terrible. I will write this better. This still equals to f prime of c equals to this, because that's the left-sided limit, okay? And the limit, so at this point we have proven that f prime of c is less than or equal to 0, and f prime of c has to be bigger than or equal to 0. That means, so therefore, f prime of c has to be equal to 0. It's bigger than equal to 0 and less than or equal to 0. Therefore, it has to be equal to 0. There's nothing that that's both except 0 itself. And that's how we prove that if you have an extremum, such as a maximum, then the derivative has to be 0, assuming everything is the right conditions, such as f is differentiable, of course. So that's the proof for maximum. The proof for minimum is identical, except you flip the sign around. So it is less than becomes bigger than, but otherwise it's identical, and that's how we proved Fermat's theorem. As you can see, the theorem is very neat, and a cute little theorem that is nevertheless going to be quite useful. So let's look at the next thing. Now let's go to page 370 and look at example 412, 4.12. And example 4.12 has 3 parts. I will do part A, and I'm assigning the rest of the parts to to your homework. Please do these. They are good practice, okay? Even though they are pretty straightforward and there is not much to it, but I will do one anyway. So part A says f of x equals to 1/3 x cubed minus 5/2 x squared plus 4x, which is a cubic function. And then, so what are we supposed to do with a cubic function? Well, we are supposed to, what are we supposed to do here? Find all critical points. And then figure out whether each critical point is a maximum or minimum. Okay, now what is a critical point? We just mentioned that a critical point is when the derivative is 0 or undefined. Okay, that is something 0 or, well, something wrong with it. So that's the critical point. All right, so let's see how we want to do this. Mostly the derivative is 0 is what we're interested in. So figure out when is the derivative is 0. First, we'll take the derivative. So f prime of x equals to 3 times 1/3 x squared minus, drop the 2 down, 5x plus 4. That's the derivative. And then we need to set this equal to 0 to find the critical points, or see if it goes crazy at some point. Well, we'll worry about crazy later. Okay, right now this is fairly straightforward. We'll do this this trick. Okay, that is minus 4 minus 1 multiplies to become 4 minus subtracted together become 5. So so we have the bunch of x's, and then all right, so at x equal to 4 and x equal to 1, something interesting is f prime is 0. So what is okay, that's fine. Now, and then what we're gonna do is graph this thing on the Desmos graphics calculator, which will show you what happens at these points. And once you graph this thing, right? Then you can see that what am I seeing? At 4, it has a minimum. At 1, it has a maximum, local, both local. And after that, the graph takes off. And then that's that's about all there is to say about it. So please finish the problem, the example when you do homework. And with that, we will move on to the next question, is finding the absolute maximum and the absolute minimum. Well, is if you have a closed interval, as we mentioned earlier, actually I should mention this. There's another theorem Next page, page 372. That says that if you have a function and in a closed bounded interval, so your function is limited, okay, like this, and but you're limiting it to a certain amount of x. Okay, you're only looking at it in a closed area. If you look at it that way, then the function is guaranteed to have at the absolute maximum and the absolute minimum will happen either at the endpoints or at some kind of a critical point. Assuming the function is continuous, I guess. Yeah, they're talking about continuous, which is fine. But we actually care about differentiable, but we'll go with continuous just to include all ends. If you have a continuous function, but in a limited bounded, closed bounded interval, so contained endpoints, then the function's maximum and minimum has to be somewhere either endpoints or some critical spot. Yeah, okay. So that's that. That's good enough. Okay. Now let's look at the next thing. So example 4.13 is very straightforward as well. You just calculate something. You're given a function, you calculate the derivative and figure out when is this 0. Those are the critical points. And then you check the endpoints on some finite interval to see who's the absolute maximum, absolute minimum, and then who's the local maximum or local minimum. And yeah, and that I will have you do as homework as well. Example 4.13. So for this section's homework, I have chosen problems number 101, 103, 111, 115, 119, 123, 127, 133, 131, 133, 35, and 39, which I will also post below the video.